Alright, what's up everyone? Welcome back to Structure-Free Learning. And in this video, we're going to look at thermal stress and axially loaded members. And specifically, what we'd like to be able to do by the end of this video is calculate the effects. And when we say effects, we're talking about stress or reactions, internal loadings of an axially loaded member that is subject to some sort of temperature change, whether it's a temperature increase or a temperature decrease. And what we know, or at least what we have a sense of, is that when there is a temperature change, if the heat goes up, then it tends to expand. And if the temperature decreases, it gets colder, brr, then it contracts. And at least that's the sense that we have from our experience in doing whatever it is that we do that causes things to heat up or cool down. For us, in an engineering, application, this deformation is typically linearly related to the temperature change. At least that's what we observe experimentally. And for a homogeneous isotropic material, so homogeneous means it's the same throughout, isotropic has got the same material properties in all the directions. This axial deformation is alpha times the temperature change times the original length. This coefficient of thermal expansion typically has the units of 1 over degree C, or some people like to say strain per degree C, but you know that millimeter per millimeter, or that the normal strain is dimensionless. So a lot of times people will give the number as 1 per temperature, 1 per degrees Fahrenheit, or even 1 per degree Kelvin. And then that delta T is the actual temperature change. If the temperature is increasing, then it's a positive change. If the temperature is decreasing, then it's a negative change. Here, this lowercase delta T is the axial deformation, or the change in length that occurs due to the temperature effect, and L is the length of the material. Now, something that we want to distinguish is that if I have a statically determinate member, it's free to expand and move around, and there's going to be no stresses that are going to occur inside that structural element. So if I have a uniform temperature change, this thing is going to be free to expand on its own, no thermal stresses in the statically determinate structure. But if it's statically indeterminate, and I'm again experiencing this uniform temperature change, now my member or my component is no longer free to expand the way it wants. It's constrained, and it's going to have stress. As it relates to us in a first course in mechanics of materials, when I have something that's axially loaded only and experiencing a uniform temperature change, I will only develop stresses if I have a statically indeterminate member. Then I'm going to use the same methods I use for statically indeterminate structure with loading on it, coming up with compatibility equations, or using the force method to come up with the compatibility equation to solve out for the effects. And when we say effects, we're talking about stresses and reactions, whatever we need to know so that we can understand what's going on with this structure. Alright, so that's our brief introduction to thermal stress and axially loaded members. There's no use in this equation unless we know how to use it, so let's do a practice problem next. Structure free!